Welcome to Math 1314. This is section 6.2. It's sort of a continuation of the matrix method into, well, what can go wrong? We've seen in the previous section what can go right, and that is we can get ones down the main diagonal. And if we do that, the answer for x and y appears there on the right hand side, giving us one solution to our system of equations. But two other possibilities do exist. We could, when we try to solve our matrix, get a row where I've got 0, 0, and something that ends up not being 0. For example, let's say I had 1, 2, 3, 0, 0, 4. Well, that would mean 0x plus 0y is equal to 4. Well, the left-hand side is 0, so 0 equals 4. Well, that's not possible. So what's going on? Well, what's going on is this particular system of equations are really two parallel lines. Therefore, they never cross and there's no solution. So if we get a row of all zeros and something on the right is not 0, that means we have no solution. The other possibility is we could get an entire row of all zeros. So for example, we could have 1, 2, 3, and then a whole row where all parts, even the right hand side, are all zeros. If that's the case, then we have an infinite number of solutions because we have the same line and the two lines are actually sitting on top of each other, intersecting at every point. Alright, so let's take a look. In question 1 here, we have our system of equations 2x plus 4y is equal to 5. X plus 2y equals minus 3. Alright, so we convert that to our matrix, grabbing just the coefficients. I see there's a 1 there. That's good. So I'm going to swap out row 1 and 2. Alright, now our goal is to use that 1 to make a 0, as we did in the previous section. So I'm going to take minus 2 times this row and then add it to row 2. So minus 2 times each of those numbers, we get minus 2, minus 4, 6. Here's row 2. We're going to add these two together to get my new row 2. Well, when I do that, I see that what we have is 0, 0, 11. So 0 would be equal to 11. That's just not true. So what I did over here, you don't need to do this. I'm just showing you that if you isolate the y in each equation, let me scroll up a little here. If you isolate the y for each of the lines, you get that they both have exactly the same slope, minus 1/2 x. They have different y-intercepts, so they are parallel lines with no solution. And so if I come back up here, the system has no solution. Alright, in question 2, we have 3 equations and 3 unknowns. Alright, so I grab all the coefficients, 1, minus 3, 14, and 5. Do that same thing for the second equation and for the third one. I already have a 1 in this position, so I'm going to use this 1 to make 2 zeros. So I can simply add row 1 and row 2 to make a new row 2. And so I get 0, 1, minus 4, 4. I'm going to need to multiply row 1 by a minus 1 so that when I add it to this one, I get a 0. Alright, so that's minus times row 1 plus row 3, and we get our new row 3. Alright, so here's the new row 3. Here's the new row 2. So we had a 1. I made 2 zeros. I've got a 1 now. That's good in this position. I need to use it to make zeros above it and below it. Let's see, I can multiply it by 3. When I add it to minus 3, I'd get 0. I can multiply it by 2. So 2 add minus 2 is 0. And so let's do that. Alright, and so I've got 2 times row 2. Here's row 3. I added that up, and then I put in my new row 3. Now I didn't actually need to make a 0 above it because my new row 3 is 0, 0, 0, and something on the right that's not 0. Remember, if we have a whole row of all zeros, that means we have an infinite number of solutions. But if we have something that's 0, 0, 0, and not 0, then our particular system of equations has no solution. Alright, and in question 3. In question 3, we have our system of 3 equations and 3 unknowns. I convert that to our matrix. I see there's the 1 I want, so I'm simply going to swap out row 1 and 3. So good, got a 1 where I want it. And now I'm going to use the 1 to make 2 zeros. Let's see, minus 4, add 4 would be 0. Alright, so I'm going to take minus 4 times row 1, there it is, add row 2, and we get our new row 2. So here's the new row 2. Let's see, 5 times row 1, add row 3. Alright, so do that. So here's my new row 3. Now, when I did that, that's good. We got the 1 and 2 zeros. I'm looking at row 2 and row 3 and noticing they seem to be exactly the same. Alright, well, let's continue and see what happens. They do look exactly the same. So I take row 2 and divide by 2. Alright, so here's my new row 2. And now I'm just going to proceed like normal. I'm going to take the 1 here and make some zeros above and below. So I simply need minus 2 times this row and then add it to row 1 and row 3. Alright, so when I take minus 2 times row 2, add row 3, I see here's my new row 3. And I get this situation of all zeros. Now I go ahead and finish off getting a 0 above it because when I have an infinitely many solutions, the solution is what we say dependent. And I'll show you that in a moment. So let's just go ahead and take this 1 and get rid of the 2 above it. So minus 2 times row 1, did that, and now plug that in. Alright, so there's my row of all zeros. Now what does all this mean if it's a row of all zeros? Well, let's take 0, 1, 3, minus 7 and put back in all the variables. So 1y plus 3z equals minus 7. And if I solve it for y, I get this relationship for y that depends on z. And if I take the top row, I get 1, 0 to 11. So 1x plus 2z is 11, or x is minus 2z plus 11. So my x and y depend on z. So my answer is supposed to be a point, but I have an infinite number of them, so I need a way to generate them all. So I simply write down what I know about x. It's minus 2z plus 11. I write down what I know about y, minus 3z minus 7, and z is just z. We call z a free variable, meaning now I can pick different z's, and as I pick different z's, I'm going to generate all of these points where they intersect. And so we get the system has infinitely many solutions, and the solution set is this item where z is any real number.